In the test tube is an aqueous solution containing ions of silver, lead, and copper. When we add chloride ions, a precipitation occurs, producing solid silver chloride and solid lead chloride. The copper ions remain in solution, indicated by the blue color of the liquid, which is decanted. We add distilled water to the test tube and heat it. Lead chloride is soluble in hot water and returns to solution. We again decant the solution in the test tube, leaving solid silver chloride. To demonstrate that the decanted solution contains lead ions, we can add chromate ions, which cause the precipitation of lead chromate. The characteristic yellow color of the precipitate confirms the presence of lead. We have separated the three ions in the original solution from each other.
This video is pretty cool. You start with a test tube that contains copper 2+, silver plus, and lead 2+ ions. And the goal here is to separate out all three of the ions, one from each other. So you'll have just a test tube of copper, a test tube of silver, a test tube of lead. Now, I say to separate out, we're going to separate out most of it, all right? Like we talked about earlier with the mercury example, we probably won't get all of it out, but we're going to get a lot of it out. And using some simple tests, we can kind of make sure that at least most of the ions are separated out from each other. So that one caveat aside, this is pretty cool. First thing they did is they added a source of chloride. All right, you could add HCl, you could add NaCl, but the reason they did that is AgCl and PbCl2 are very insoluble. So they quickly made like a white solid and they decanted. Decant means to pour the liquid off carefully and keep the solid in the test tube as much as possible, okay? And so the stuff they decanted, the liquid form, that had the copper ions. And copper 2+ has a very powerful blue color, which you can see on the left test tube right there. So that's how they separated out the copper. Copper 2 chloride is not very insoluble. It's very water soluble, as a matter of fact. Most chlorides are AQ unless they're with silver, lead, or that mercury thing. So that got the copper out. Now the next thing is they needed to separate out the silver chloride from the lead 2 chloride. And this is something we'll talk about later, but lead 2 chloride actually dissolves pretty well at higher temperatures, while silver chloride does not. So they took the test tube with the AgCl and the PbCl2 and they placed it in boiling water. And the PbCl2 went into the liquid phase. It actually dissolved, all right, while the AgCl did not. So again, they decanted out the liquid from the solid. The liquid should have PbCl2 and the solid should have AgCl. But to make sure that the liquid phase had PbCl2, they added chromate. And chromate with lead makes a really bright yellow color. It's a pretty cool color, actually. So that proved, if you will then, that the lead had been transferred to the new test tube. The only thing different I would have done here was I would have added chromate to the silver test tube as well. Silver and chromate makes kind of a red color, so you could have confirmed and stuff that that was there. But either way, no big deal. This is how chemists separate out ions from one another. It's a pretty good value, all right? Most of the silver is separated from most of the lead, from most of the copper. Probably not all, all right? If you really were worried about any of those, you'd have to do something a little greater. But at least to the first order, this is a pretty cool way to separate out one from the other based on differences in KSP. Now, the difference in temperature, solubility, is something we'll talk about more in the next chapter. But for right now, just realize that some compounds, it's easier to dissolve them at warmer temperatures than other ones, and that's something we'll see later. So this is a kind of question you might see, all right? We have a solution and it has 0.020 molar silver ions and 0.020 molar lead 2+ ions. And we want to separate the two of them out. Now, chromate is a great thing to add, great polyatomic ion to add here, because both red Ag2CrO4 and yellow PbCrO4 are insoluble compounds, but they're not soluble to the same level. And here are the KSPs for the compounds that form, and you can see that there's a little difference between them. They're not the same number, all right? So In a question like this, it might be nice to know if we added chromate in really, really small amounts, which would we see first? Would we see the yellow PbCrO4 or would we see the red Ag2CrO4? And we can absolutely solve for this. Now, what we're going to do is we're going to have two kind of simultaneous equations going on at the same time. One will be the KSP for Ag2CrO4. So this 9.0 times 10 to the minus 12 number, that's going to equal the silver ion concentration squared. And this is the silver ion. And we're going to solve for chromate, okay? In the other set of equations, we're going to use the other KSP, the 1.8 times 10 to the minus 14th. That equals the lead 2 plus, which we're also given, 0.020, and we're going to solve for chromate there. Once we have the two values of chromate, one of the numbers will be smaller than the other one. And the smaller value, that's going to be the indication as to which one precipitates out first. Because if we add really, really small amounts and we add just that smaller number, that's going to make a solid. The one that needs more chromate is going to take extra chromate to make a solid, and that one would precipitate last. So again, the math is not too hard here, but thinking it through can be a little bit weird. Remember that the substance whose KSP, the values there, is first exceeded will precipitate first. So we really kind of want to solve for the chromate here. We want to see which one is going to take the least amount of chromate. Smaller amount of chromate will be the one that precipitates first. We're going to calculate again the chromate required by each ion. So let's do the silver chromate first, all right? So KSP for silver chromate equals silver plus squared times chromate, and we want to solve for chromate. So chromate will equal the KSP number, this thing, divided by the silver ion squared, because it's squared because of the 2 right there. The chromate required, 2.3 times 10 to the minus 8th moles per liter. And that's a very, very small amount of chromate. It's not going to take much chromate to make the red Ag2CrO4 precipitate out. But we should check the lead 2 chromate as well, of course. So let's do the same kind of calculation, but for lead 2 chromate. Lead chromate, KSP equals Pb2 plus times chromate, or chromate equals KSP, the number given, divided by the lead, that number, and lo and behold, 9.0 times 10 to the minus 13th. Well, if you compare these two numbers together, the chromates required, you can see it actually takes quite a bit less chromate to make PbCrO4 precipitate than it does the silver. If we're adding very, very small amounts of chromate, if we added 9.0 times 10 to the minus 13th moles per liter chromate, that will make the yellow PbCrO4 precipitate out. On the other hand, we have to go many orders of magnitude higher, i.e. 10 to the minus 13th to 10 to the minus 8th. We have to raise that chromate several orders of magnitude to make the red Ag2CrO4 precipitate out. So PbCrO4 should be the first one to make a solid. So this question, we have 0.1 molar potassium sulfite and 0.30 molar sodium sulfate. Now, sulfite is SO3 and sulfate is SO4. And we're slowly adding in calcium nitrate. And the question is, which precipitates first, calcium sulfite or calcium sulfate? Okay. There's an unofficial way and an official way to do it. Let's talk about the unofficial way first, all right? Calcium sulfite and calcium sulfate are both 1 calcium to 1 polyatomic ion, 1 to 1, all right? And the concentrations of the sulfite and sulfate, 0.10 and 0.30, are pretty close to each other. Most of the time in these cases then, smaller KSP will tell you which one precipitates first. So because the calcium sulfite is 1.3 times 10 to the minus 8, and that's a lot smaller than the 10 to the minus 5, I'm going to predict that calcium sulfite is going to precipitate first. That's the unofficial way. Smaller KSP often means precipitate first, while larger KSP would mean precipitate last. Now, the official way to do this would be to set 1.3 times 10 to the minus 8th calcium sulfate equals the calcium, our unknown, times sulfite, and sulfite is 0.10, and you'd solve for calcium. You do the same thing for calcium sulfate. 2.4 times 10 to the minus 5 equals the calcium, the unknown, times 0.30, the sulfate, and you'd solve for calcium. Either way you do it, you're going to see calcium sulfite is the smaller one. I didn't even do the math on this one because, again, sulfite and sulfate are both within in the same order of magnitude. And the difference in KSP was quite a bit, about 3 orders of magnitude. So sulfite and sulfate really aren't going to make a difference. Calcium sulfite is going to precipitate out first. And if you don't believe me, absolutely go through the math. You would take 1.3 times 10 to the minus 8 and you divide by the sulfite, 0.10. You do the same thing for calcium sulfate, but you take that KSP and divide by 0.30. And you should see that this one is smaller than the other one. Again, that 10 to the minus 8th versus 10 to the minus 5 makes a big deal. Here's a question that's similar to the last one. We have a solution now, 0.020 molar silver ions and 0.020 molar lead 2+. We saw that PbCrO4 in the earlier example precipitates first. There's the KSPs. This is another kind of twist you can put on these kind of problems. If you really want to separate out the silver from the lead, how much lead remains in solution when the silver plus just begins to precipitate? This is another kind of common question you might see. You really want to get the lead out of the silver. And as you start adding chromate up to the point where the silver chromate crashes out, then you can actually start pulling the lead out. You can use decanting or you can filter it, stuff like that. So remembering that lead started at 0.020, let's see how much is left when the silver ion begins to precipitate. From the last example, the chromate required to make the Ag2CrO4 2.3 times 10 to the minus 8. So what we're going to do is we're going to solve for lead at this point. We're going to go back to the KSP for the PbCrO4, but we're going to put this number in for the chromate, and we're just going to solve for the lead. Mathematically, it's not hard, but sometimes thinking about these things can get a little weird. So if you do that, the KSP was 1.8 times 10 to the minus 14th. We're going to divide it by the chromate needed to make the Ag2CrO4 precipitate, 2.3 times 10 to the minus 8th. And lo and behold, 7.8 times 10 to the minus 7th moles per liter. So what that means, if we add 2.29 times 10 to the minus 8th moles per liter chromate, our lead ion, which started at 0.020 moles per liter, went down to a number much less than 10 to the minus 6, all right? It's like 10 times 10 to the minus 7th would be 1 times 10 to the minus 6. So a pretty small amount. And in the chemistry world, that would be separating. Obviously, the concentrations didn't go to 0. That's the joy of equilibrium, but at least it's a lot less than it was.